In this lecture, we'll be studying about process scheduling. So in the previous lecture, when we studied about process control block, we came across a topic called process scheduling. And I told you that this topic is very important, as well as operating system is concerned. So before we move ahead in this lecture series, I want you to have a brief idea of what process scheduling is, so that whenever we use this term, you may not be blank, but you will know what it actually means. So this is not the whole topic by itself, but this is just to give you a brief idea of what process scheduling. Alright, so let's see. What is this? So here it says, the objective of multi-programming is to have some process running at all times to maximize CPU utilization. So we have already talked about multi-programming in the beginning of this lecture series, and the objective of multi-programming is to have some process running at all time to maximize CPU utilization. So what does this mean? So let's say that we have the CPU. And let's say that we are using only some percentage of the CPU. Let's say that we are using only 20% or 30% of the CPU. So if we are doing that, we are not making complete utilization of the CPU. And hence we can say that we are wasting our resources. So the objective of multi-programming is to have some process running at all times. We want to have at least some process running at all times so as to maximize the utilization of our CPU. And hence we can say that we are efficiently using the resources that we are having. So that is the objective of multi-programming. Now you may ask, how is this related to process scheduling? Don't worry, we will come to that, and you will understand how it is related as we move ahead. Now the next thing that we will be talking about time sharing. The objective of time sharing is to switch the CPU among processes so frequently that users can interact with each program while it is running. So time sharing is also something we have already talked about in the beginning of this lecture series. And the objective of time sharing is to switch the CPU among processes so frequently users can interact with each program while it is running. So let me explain this using an example. So let's say that in your computer, you are typing a document using your Microsoft Word, and at the same time, you are listening to music using any of your music players, let's say Windows Media Player, and at the same time, you are downloading some files using your Chrome browser. So we see that you are able to do all these three tasks. At the same time, you're able to type the document. At the same time, you are listening to music, and at the same time, the file is being downloaded in your browser. So we feel like we are doing these three things at the same time, but if you go deep into it and really look at it, we'll find that these three things are not actually happening at the very same time. But what is happening is, the CPU is switched among these three processes so frequently or so quickly that you are able to actually interact with each program while it is running. So according to the human speed, if we look at it, we feel like this. Three things are happening at the same time. But actually it is not. But the CPU among these processes are switched so frequently and so quickly that we don't actually realize that. And as a result, you are able to interact with each of these programs while it is running right. So those are the objectives of multi-programming and the objectives of time sharing. Now in order to accomplish these objectives, what shall we do? How are these two objectives accomplished? So to meet these objectives, the process scheduler selection available process, possibly from a set of several available processes for program execution on the CPU. So in order to accomplish these objectives, we have something known as the process scheduler. And what does it do? It selects an available process from the set of available processes that we have for program execution on the CPU. So we have several set of available processes that are ready to be executed, and the process scheduler will select an available process, and it will assign the CPU to that process so that it can begin its execution. And what will happen when a process is being executed? Will it be allowed, or will it be given the complete time to complete this execution? Or if another process comes with higher priority, will that process be given the chance to execute and the other one has to wait? All these things will be decided by the process scheduler. So that is where process scheduling is important and where it comes into play. So for a single processor system, there will never be more than one running process. If there are more processes, the rest will have to wait until the CPU is free and can be rescheduled. So as I told you, in a single processor system, there will never be more than one running process. There will be only one single process running at a particular time, though it may look like there are many processes running at the same time. But in a single processor system, only one process will be running at a particular time. But what happens is, the CPU is switched so frequently among these processes that we don't even realize that. And as I told you, if there are more than processes, then the rest will have to wait until the CPU is free and can be rescheduled. And who will take care of this? The process scheduler will take care of this, as of who will be executing, or which process will be executing, and which of them will have to wait. And if higher priority process comes, then which will be executing. So in order to help with this process scheduling, we have something known as the scheduling queues. So basically, there are two kinds of queues, which are the job queue and the ready queue. So first we have the job queue. So what is this job queue? As a process enters the system, they are put into a job queue, which consists of all processes in the system. So when the processes enter the system, they are put into a queue known as the job queue. So job queue consists of all the processes in the system. They may not be executing at this time, but these are the list, order set of all processes that we have in the system. So all these processes, they are put into this set, or this queue, known as the job queue, where they will be waiting in order to go to the ready state. The next queue that we have is known as ready queue. The processes that are residing in main memory and are ready and waiting to execute are kept on a list called the ready queue. So in ready queue, we have those processes which are ready and waiting to be executed. So these are processes that are residing in the main memory and they are ready to be executed. They are just waiting to get the CPU so that they can start executing. So job queue is the list of all the processes that we have, and ready queue is the list of processes that are ready and waiting to be executed. They are just waiting for the CPU. And once they get the CPU, they can start their execution. Now once the processes are in the radio queue, and once they receive or get the CPU execution, let us see the things that can happen. So this diagram here shows what happens to a process when it goes from the radio queue into the running state. That means when it gets to CPU, and what are the things that can happen. So here let's say that from the job queue, the processes, they come to the ready queue. So let's say that a particular process is the ready queue, and it is just waiting to get the CPU for its execution. So once it gets the CPU and it begins its execution, there are several things or several cases that can occur. So the first thing can happen is it received the CPU and it completed its execution, and the process just ends. That means it goes to terminated state. So there is one thing that happen from the RDD. It got the CPU and completed its execution, and it has ended. Now another thing that can happen is it comes from the RDD and it is assigned the CPU and it is holding the CPU for its execution. But at the same time, let's say that there is another process that comes with higher priority. That means this process that comes now is having higher priority and it has to be executed before this. So what happens? The process that was previously executing, it will get swept out, and it goes to a list called the partially executed, swept out processes. So it comes here, where it is swept out because another process of higher priority came, and it has to be executed before that. So it is swept out, and it comes over here, and after that, it gets swept into the ready queue again. So the execution is not completed fully, it is just partially executed. So it still needs the CPU to complete the execution. So it comes back to the ready queue, again waiting to receive the CPU. So it waits for its turn, and according to the process scheduler, when it is assigned the CPU again, it will come and it will get executed, and when it is completed, it will go to the terminated state. Now another thing can happen again is from the RDD, it is assigned to the CPU and it begins execution, and at some point of time it needs some input output devices. So we have discussed about output devices. So at some point the process may need to use some of the output devices. So what it will do, it will go to the input-output waiting queue, where it will wait for the input-output operation to occur. which is required by that particular process. So if the input-output devices are available at that time, that operation can immediately occur and can continue its execution. But if the input-output devices are being held by some other process, and if it has to wait, then this process will come to the input-output waiting queue and wait for the availability of that output devices. And once that input-output devices are assigned to the process, it will execute the input-output operation. So the input-output operation will be executed. And once input-output operations are executed, it will go back to the ready queue again because it needs the CPU again to resume its execution. So here it waits for the input-output devices. And once it gets it, and once operation is done, goes back to the radioc and waits for the CPU again to resume its operation. And once it receive the CPU, it resumes its execution, and it can, and so that is how a process comes from the RADIC. And once it receives the CPU, those are the cases that can happen during the course of its execution, and then which process will come, and then which process will assign the CPU at what time. All those things will be decided by the process scheduler. So this is just a brief idea that I want to give you about process scheduling. And I hope that was clear too. Thank you for watching, and see you in the next one.